Hello, everyone. Welcome to the KIE Live number 30.
Really, 30?
Already.
Oh my goodness.
And
Aw-
today we are here. Please go on.
Go.
Yeah, today we are here to talk about one of the initiatives that the KIE group is bringing to the community, which is about Trusty AI and how we can actually trust more the system that uses AI and predictive predictive modules. So, uh, we are going to learn a little bit more about the concepts, the basic concepts, and about the algorithm that runs underneath it, which is Lime.
Yeah, and it's very interesting the all the topics that we touch in the key group, right? We have business automation as an umbrella topic, and we have a lot of specialized topics. We have the mathematical optimization with planner, we have business process, we have the Drools, the DMN, and today we will learn a lot about this initiative that we have. This is the Trusty to understand where AI can fit in this business automation umbrella. And for that, we will have today our special guest, Tommaso. Um,
Teofili. I always like to do this with our Italian guests, and they hate it. I know they hate it. It's just a thing. It's been around for a year, sort of a year and a month right now. Just kidding, yeah, but a year. And he's been really helpful and he's really engaged and sharing lots of knowledge also on the Key blog. You can jump over there, just take a look at what's coming, not only on the TrustyAI initiative, but all the projects that we work with, jBPM, Drools, OptaPlanner, and Cogito. So with that being said, we should bring our guests to stage. Hey, Tommaso.
Hi everyone.
How are you doing today?
Good. I'm doing good. How about you?
I'm doing great. Thanks for asking. I'm looking forward to your presentation because it's a mix of the basics around explainable AI and a little bit more about the algorithm. So Lime is the algorithm that runs underneath it to actually make explainability possible. Is that right?
Yes. So it's one of the algorithms in the explainable AI landscape, and actually one of the most widely used. So we will go a bit through an introduction about explainable AI, and also have a look at the basics around Lime and how we within the TrustyAI initiative did some optimizations to the way Lime works in order to make it more robust, especially for the case of business automation and decision services.
Yeah,
that's
this is pretty interesting.
yeah. So this when you talk about decision service, I just come out of my mind is like DMN. So we'll be able to explain what's going on, the decision behind that, right? In a black box way, right? We don't
Exactly.
instrument the what's happening there. So we black box, and it's very interesting to see how you do that.
Yeah, so that's one of the great things about using um, black box explanation.
I'm just kidding here with Donato. He explained me that I was using like bambino wrong. I shouldn't say bambino to grown up men. Now I know it.
Oh, no problem.
Awesome. So, Tommaso, will you please share your screen so we can get started?
Sure.
So today's session is going to be less than an hour. So if you're watching, stay around and learn a little bit more about the explainable AI and the robust local explanations that can be used for these black box models.
And we are here to support with questions. If you have any questions, we will help Tommaso to bring your questions to him.
Okay. So thanks, Karina. Thanks, Alex. So let's get started. So as we briefly introduced, we will talk today about robust local explanations for black box models. This might sound a bit complex title, but in reality, what we want to look at is to look at getting our predictive models, be them decision services or AI-based systems to be trustworthy. So our main goal today is to gain a better understanding of how those systems that might be a bit opaque to the end user work internally, or at least to understand the rationale behind their predictions, and also possibly a more coarse-grained behavior of how the model works as a whole, or how the decision service works as a whole. So not just on a single prediction. So these basically are the main goals of Explainable AI. As the name implies, Explainable AI comes, or at least focuses on artificial intelligence-based systems, but it's very suitable for any kind of opaque systems that demands for a more transparent decision making. So let's use a simple analogy. So if you think about a car versus a bicycle, you can easily understand that the bike seems more interpretable with respect to the car. So if we look at the bike going, we can easily get how it works. Whereas if we look at a car, first thing is that the engine is hidden. And even if we open the engine box, it's not, at least as a first sight, very easy to understand how the engine works, unless you are a mechanic or something like that. But let's get it to a level where the important part is humans being impacted. So let's talk about two opaque systems. So one system is again the car with its engine. The other opaque system is a self-driving system. So as you can imagine, if the engine breaks, it's a problem. If the engine works, that's all good. But on the other hand, if the self-driving system doesn't work, it's not the same as the engine doesn't work, because not working for the self-driving system is actually much more dangerous for the human. So would you trust the self-driving system to drive on your behalf while you read a book? So this is the type of questions that Explainable AI is there for. So we now go deeper into the business of Explainable AI. So let's look at predictive models. So for our predictive model that we want to use to be trustworthy, it either has to be transparent, so we can look inside and it's easy to understand how it works. Things like a simple rule-based system with one or two rules. Or alternatively, it has to be explainable. So there has to be a way to get an explanation of either a single decision, a single prediction that is generated by such a model, or over the model as a whole. So Explainable AI focuses on providing explanations of artificial intelligence-based systems. As we said, these also can include decision services, so DMNs, for example. And here you can see a few different visualizations that are generated as explanations for decision services. When we talk about explanations, there are actually different methods of explanations. So Saliency methods like Lime and SHAP and other methods from Explainable AI explain the impact of each feature on a specific predicted output. So in this example here, we have a credit card approval system, and we simply get an input this system, provide an input, and get an output. So the explanation tells us, in this case, it was a rejection, that some features in the input had a negative impact on the result, whereas some other features had a positive impact. For example, for the rejection, the value of age was particularly important. So, for example, if the person who requested the credit card was too young or was too old, that was probably the reason why the request was rejected. So these kind of visualizations on predictions helps the user getting trustworthiness on the prediction. There are actually other types of explanation methods. Some of them are called feature relevance methods. In practice, they are the global counterpart of saliency methods, which means that basically the explanations, again, comes in the form of an importance score for each feature in the input space. But instead of those importance scores being tied to a single prediction, they're actually tied to the whole model. So, for example, a given model might give too high, for example, in the model on the right-hand side, a too high importance to a feature was about the ethnicity of a person. In this case, this might raise fairness concerns, which are things that are very important to detect when models are to be used with real humans. Other kinds of methods are exemplar methods. One example is called counterfactuals method, which basically answers the question, what should I change in the inputs and how to obtain the desired output? So if we think back to the example of the credit card approval system, that a counterfactual explanation might come in the form of, hey, you should change your age from 16 to 21, for example. So basically, come back in 5 years. So as we said, goals of explainability are increasing trust in the decision-making processes where predictive models are involved. They want to make it easier to understand the behavior of predictive models for end users. And as bonus, we want to be able with explainability to detect any possible bias in the model, or eventually detecting fairness concerns. Now, we will have a look at one of the explainability methods that we mentioned, which is called LIME, which stands for Local Interpretable Model Agnostic Explanations. This method was proposed in 2016 by Marco Tulio Ribeiro and others. And now we will have a look at how it works. So as we said, LIME is a saliency method. And the way it works is that it trains an interpretable model out of the uninterpretable model in the neighborhood of the prediction input. What we mean by neighborhood, we will have a look in a second. And after having trained such an interpretable model, it generates an important score, a weight, for each feature in the input. One important advantage of using LIME is that the model, the system that we want to, whose prediction we want to explain, can be treated as a black box. So we don't need to know whether it was a decision table, a neural network, or what kind of other system. So this simple graph tells us how LIME works. So given a prediction, so an input with its features and its corresponding output generated by the system, the decision service, for example, it generates copies of the input, and then it perturbs those copies. By perturbing, we mean that, for example, if there are text features, some words in those text features are dropped. If there are numerical features, the numbers are slightly changed. If there are categorical features, values from one category are replaced with other categories, and so forth. After having perturbed the copies of the input, basically the system, the model, is executed, is called on those perturbed input copies. And at this point, the interpretable model is generated. In order to be interpretable, the model is sparsified so that we can actually look at what kind of features are available or not available in a given perturbed example. Fine. Before training the linear model, the weight samples are calculated. So basically, given an input, the prediction input to explain, we give more importance to those perturbed input which are closer to the original input. And finally, those weights are used to train the linear model on the sparse data. The explanation is, in the end, composed by the weights of the linear model, and they are used as we said, as feature weights.
Tommaso, sorry to interrupt you.
Yeah.
We have a question about the trained linear model. Stefano is asking if the trained linear model means a neural network being trained.
No. I mean, what we mean by a linear model, it could be things like ridge regression, or I don't know, a perceptron, or this kind of models, which basically do not. You can think. So you can have a look actually in this slide that I'm sharing, a linear model. So you see that the actual model to be explained is non-linear. So the decision boundary of the model to be explained is you can see that from the blue versus red part of the figure. However, what we want to learn is basically a line that separates positive examples from negative examples. What we mean by that is that, so if that answers the questions, I will go ahead. Otherwise,
yeah, I think so. Hopefully, Statues, you can use the comments if you have a follow-up question. So I let you continue. Thank you, Tommaso.
Thank you, Alex. So in this example, in this figure here, we have, for example, that the bold red cross is the input to be explained. So we have a prediction, and that bold red cross is the input to be explained. So what Lime does is to sample, so to generate other inputs which are as similar as possible to that bold red cross. So you can see that there are crosses and bubbles that are generated. And actually, after having generated those inputs, it calls the model on those inputs. So the inputs that were predicted as true, for example, are marked with a red cross. The inputs that were predicted as false, for example, are marked as a blue bubble. Additionally, you can see that the closer the input is to the bold red cross, the bigger is the cross or the bubble, which means that we give more weight to the inputs that are closer to the original input. And finally, the line that we see here is actually the local linear model, which is used for trained. So the output is, again, this sort of feature score chart. The way it's generated is, for example, in this scenario here, we have actually only two features. So this is, of course, a simplified examples. So, but if we would have two features, we would have that one of the weights comes from the intercept of the line, and the other on the angle of the line. So the semantics of Lime. So what we mean with positive and negative scores. So when the model to be explained is a classification model, so it's a classifier, like in the credit card approval system, the positive score for a feature means that the feature is important for the model to predict true. And negative, of course, means that the feature is important for the model to predict false. When you have regression cases, so like, for example, I have a model that is used to calculate the risk of a given transaction, then the semantics of Lime is that a positive score means that that particular feature is important for the model to make that specific prediction value. So that specific risk score. Whereas all the other possible predicted values would lead to a negative score. All the negative score means that the model, the feature is important for the model not to predict that specific value, basically to predict all the other possible values, feature values. The feature weights do not represent probabilities, at least in Lime, whereas in other explainability techniques they do. And the feature weight range is basically infinite. So it's not 0, 1 or -1, 1. The advantages of using Lime is that it can work with any kind of model, as we said. It works with text as well with tabular data. The algorithm is quite intuitive. You can debug the explanation by looking at the generated interpretable linear model, like we did by looking at those red crosses and blue bubbles, and it's widely used. However, there are some known limitations. Stability issues. Of course, when in different runs, the process of generating samples is randomized. So in each run, you can generate slightly different feature weights because the samples are actually different. So the trained linear model is different on each, might be different on each run. One other known limitation, which is particularly relevant for the decision service domain, is that it requires training data for perturbation of tabular data, which means that we cannot use Lime as it is if we don't have the training data. And if we think about decision tables, there is actually no training data we can use. And therefore, we cannot use Lime in this scenario. And it's another limitation is that a bit sensitive to different hyperparameters of Lime. One parameter, one thing to look into, as we said, is the way the sampling is done. So in some cases, if we are unlike the number in the samples that are generated, the linear model can wrongly approximate the black box model globally instead of locally. So on the left-hand side of this figure, we can see that the linear model, so the red line, actually is much more closer to the global model, whereas on the right-hand side is much more closer to how the model works locally to the input that we want to explain. So this is something very important to get right. Another thing is that the weight that is given to each sample that is generated is very important in order to get, again, the linear model right. So in the TrustyAI initiative, we tried to address all these limitations and also to make a few more improvements to how Lime works in order to have an implementation that can work with non-flat, typed, and nest features, which is, hierarchical data is very common in the case of decision services. And of course, another important aspect is being able to work without training data. And of course, we wanted to avoid all those pitfalls with stability. And we want our explanations to be effective. So one trick we adopted is what we called adaptive sampling. So basically, if we are unlucky when we generate the samples, and most of the samples are predicted with a single class, then it's harder to get the linear model right. Let's look at this example. So say that this is our unlucky sampling scenario. So we got a few samples, and actually only 2 samples are predicted as true, whereas all the others are predicted as false. So it's very uneasy for a linear model to be able to fit correctly. So as you can see, this linear model can be the result of the training, but also this other linear model or this other linear model. Actually, it's not easy to separate this data set in a robust way. So what we did is that we have a sort of iterative algorithm that detects these situations and generate more samples, actually increasing the variance in the data that is generated. What we mean by increasing the variance is that we perturb more features at once. So in this case, it's harder, for example, to get the linear model wrong. So it's the linear model is actually a better fit of the generated samples. Another trick that we leverage is what we call proximity filter. So instead of using the weights, so using all the samples that we generate, but only giving higher importance to the closer ones and lower importance to the ones that are far away from the original input, we actually filter some of them out. So let's again have a look at these samples that we generated during our sampling process. And actually, the green cross is the input that we want to explain. So this is what the Lime implementation, or at least the official Lime implementation does, is to give more weight to the ones that are closer. So the ones that are in light red and light blue are the ones that are less important. So we'll have a lower weight. So this is again the linear model that will be fitting with this data set. Actually, with filtering, we take all those samples that are not close enough, and we simply prune them away. So actually, the linear model has less data, but the data that we use is much better. So with that, and a couple of more additional tricks, we managed to have to produce more robust explanations with Lime, with our own implementation of Lime. We can work with tabular and text data seamlessly, whereas, for example, the official implementation in Python have different implementations for those different scenarios. We use the perceptron to train the classifier, whereas this is a sort of implementation detail, but it's a difference with respect to the official implementation. And we're also working on a small additional improvement to auto-tune Lime with a few prediction, which means that we reduce the sensitivity of Lime to some of its parameters with a sort of pre-training step. And this is a very brief benchmark that we run between our implementation and the official Lime implementation. And the impact score, to make it short, is just a measure of how impacting, of how important or how faithful are the explanation with respect to a given prediction. And so a higher impact scores means that the explanation is expected to be better. So, and we sort of get much better results with our own implementation and without training data, which is a big plus. So,
sorry, that's what I will interrupt. These numbers are without the training data.
Yes.
That's great numbers. It's pretty cool. Awesome.
Thanks, Alex. So with this, I'm finished. So I'm waiting for your questions.
Very nice presentation. Thank you, Tommaso. So we have a question here from Statis. Can I use different underlying classificators? For example, SVM support vector machines?
So there have been some works that use non-linear models like SVMs for training the underlying line classifier. Let's say the disadvantage of that is that then you move it from an uninterpretable to another uninterpretable space. So you can use it. Actually, yes. So the answer is yes. The thing is that then it becomes less obvious to understand the impact of each feature. So you have to do then some further work then to generate the feature weights. But actually, there is a paper. Sorry, I don't recall the name. That does similar things using non-linear models to do the underlying line work.
Pretty nice. I have a question myself, Tommaso. So I think all this calculation is probably done in memory when running on Kogito. And does it run within the same JVM that is processing the decision, or do we have a separate component for the trustee capabilities?
No, it's actually a separate component, and I mean so this is part of probably a more generic talk about TrustyAI and its architecture, but yeah, actually this happens in a different JVM, and so there is a TrustyAI service that is whose purpose is exactly that, and actually there is a different endpoint that is used to do the explanations, because as we have seen, so Lime needs to call the model to produce the sparse linear data set, so to generate the outputs. So in order not to, let's say, kill or overload the model that is used in production, there is actually a different endpoint, which actually the implementation is asynchronous in order not to block the actual, production code running on those services.
Very nice. By the way, I already stopped sharing your screen, okay, Tommaso? Just so you know.
Thanks.
Awesome.
Yeah,
so any other okay, so there's one more question here. Let me bring this one, Alex. So also from Statis, are the explanations available at the same time frame as the outcomes of the decision services, or is it a separate step, or is there a separate step required to explain the results?
So the way we do it as of today is to have actually a separate, necessary. It's done in a synchronous way. So you get your model prediction, so you use the decision service, and then on the back end, in a synchronous way, the explanations are generated, and then you can visit afterwards but they are not generated synchronously together with the results, so the actual outputs. And this is exactly done not to, let's say, overload the decision service.
Mm-hmm. Yeah, and then you go to the console and you have this information to explore and not impacting the production system that's running real customer workload.
Yeah.
And do you have any tips of how people can get started or explore a little bit more about TrustyAI, Tommaso?
Well, actually, you can have a look on the KIE blog. There are a few introductory articles on how to start with. There is actually a way. I don't actually recall the name, but if you look at the GitHub repo, there is a way to spawn a notebook and play with the Explainability API. So
the Cogito examples,
Cogito apps repo.
Cogito webs. Okay.
Yeah.
And if I recall, also, I think we introduced some Trusty setup in the Cogito docs, so you can start in.
Yes, of course.
Mhm.
There is also the TrustyAI part in the documentation, of course. Yeah, good point, Alex. Thanks.
And also we will have soon a couple of videos that will be posted to this channel, so stay tuned with explanations about a little bit more of the basics, also a little bit about Lime, and also about SHAP. So sharply additive values. Did I get it right?
Yeah.
Awesome. So, Tommaso, I'd like to thank you for being here with us today, and I'm looking forward for a future session about TrustyAI.
Thanks, Karina. Thanks to you. Thanks, Alex.
Awesome. Thank you very much, Tomas.
Yes, Donato, I will add the links later I will add it to this description of this video. Once it's out, it will probably be out this week. And yeah, sure, no problem. So that's it. That's what we have for today. Stay tuned. We are planning a session about CDS, which is clinical decisioning support. So we will do a session about a use case. It's going to be very interesting, and we'll look at it from a business automation standpoint. So stay tuned for it. So if you still didn't subscribe, if you want to know what's coming next, please follow this profile that I just shared on the link. This is the Eventbrite page where we always post any upcoming sessions that we have. Okay, so that's it. Thank you.
Subscribe, like. Thank you very much for your time, and we'll see you next week.